This is obviously a incredibly vast field. We are just going to have one little podcast in this context just to get ready for our S2S stories, or not stories. Anyway, data assimilation is exactly what it means. So when you have data, for example, they are collected, even when it's collected by satellite and it's quite large coverage of the globe, there are gaps in time and space, and satellites typically tend to be measuring something close to the surface on the ocean, land, or profiles, and in situ data, whether it's from ships or moorings or radiosondes or airplanes and so on, also tend to have gaps. So one of the ideas is to propagate the information that you have gathered into regions and times where you don't have data, and typically this can be done using models which are representing the globe, as we saw, much more continuously using parameterizations plus the equations that we are solving. So when you blend the data and the models, we call it data assimilation. Here we are specifically trying to do it to give the initial conditions at each grid point for all the variables that are needed to do the forward integration of the, let's say, atmospheric model for weather prediction, or in the case of climate prediction, typically ocean is the important player. So ocean initial conditions are provided by similar data assimilation, but now there are ideas to do coupled assimilation for initializing climate forecasts. Okay, so this is approximately how it works. Let's say this is the true state you are trying to track, this is the state of the atmosphere. Here analysis time 1, 2, 3 and so on are shown. Analysis you can think of as the first guess for the forecast in the case of the atmospheric state. So the shaded region around the true state, which is not always exactly known. That's the main problem, that neither the equations we have are perfectly able to explain the state of the atmosphere at every step, nor do we have the perfect observations. If we did, even a chaotic system could presumably be predicted forever. But considering these gaps in the equations we are solving and the gaps in the knowledge of the true state, we have to do forecast skills and face limitations of chaos and other things for predictions. So this shading here is as close to true state as observation density and observation errors allow. So this is another important thing. We have to be able to track the errors in the observations themselves, because when we mix the data with the models, those errors matter in addition to the model errors themselves as well. So there is the model forecast given the initial conditions and small corrections to short-term forecasts. So you have here a forecast. At some point you blend data at analysis time 1, you reinitialize the forecast, and then you reinitialize at analysis 2, and so on and so forth. So the effort is to stay close to the true state along the way. So always forecasts, you can see they are deviating from the true state after starting with the analysis, which is the initialized state given by the data assimilation. Okay, then comes the techniques themselves. So the system can be very detailed like this. So you are getting at, let's say, 6 a.m. you are starting your first forecast. Data is ingested, downloaded from all the available sources. Here we are showing observations, radiosondes and aircrafts being brought in. There is raw data checks done. Then observational increments at each time step is done. Quality control on the increment happens because data are coming in being blended with the data that already existed from the previous step. Some sort of objective analysis procedure is done. Analysis increments or corrections are done. So you can see now this is much more full of features that look like circulations. So that's the analysis that we talk about here. And then that analysis is given to the forecast model. So remainder of the full length forecast is shown here, so 60 to 84 hours or 126 hours and so on. And then that forecast model is corrected as we show here along the way. So next short range guess, so the analysis is given as a guess, first guess to the short range forecast, which goes back to this step and so on. So you have to keep going forward. Data assimilation techniques have evolved. There is a huge community that keeps on developing new techniques and improving data assimilation in terms of representing the errors in the data, representing errors in the models, and how to blend the data without shocking the system. For example, when you pull the system from its dynamical balance, when you integrate the model, it's balancing itself with this land, ocean, atmosphere, and then you pull it with observations as they become available, then you're pulling it away from its dynamical balance. So how to minimize these things and how to represent the evolution of the errors, that's also critical. Error covariances in space and so on and so forth. All these techniques have evolved, and parallel techniques keep going forward. What are sequential techniques like Kalman filter, or variational techniques that are better able to blend the flow dependent features, and all sorts of details exist. And this is what is called 4D VAR, four-dimensional variational analysis. There was a three-dimensional variational analysis where the errors were fixed in time, whereas now we have evolved the four-dimensional variation, which is now the best technique that exists, without going into details. So you can see here is the previous forecasts, and there is some kind of a cost function is set up to represent, let's say, the difference between the analysis, which is related to observations and blending and data assimilation, as we saw before, and how to minimize the difference between them. So globally you are driving some minimization problem as adjoint or inverse problem, let's say, in the case of variational analysis as opposed to sequential analysis. So observations come in, you use the observational cost function and the model cost functions, and you keep blending them, and you keep trying to correct the forecasts using this time evolving errors. Okay, it's hard to explain it just in words unless you know the details. So these are the evolution of the corrected forecast. So there is the initial or the previous forecast, and this is the blended corrected forecast using cost functions between previous forecast and observations to give you more skillful forecasts. Okay, there are cost issues involved, so sequential methods may be computationally cheaper, especially when they have used things like ensemble Kalman filter to better do the error covariance and its evolution in time. 4D VAR is considered very expensive, even though it's the most accurate right now, and so on. So all kinds of issues have to be dealt with. There are also evolutions in terms of what observations are assimilated. For example, the model state variables and the observed variables are not necessarily the same. So clouds are not typically observed, for example, even though now you have satellite data for it. But satellites also observe radiances, which correspond to various things like clouds, and radiances are now being assimilated into the models, even though in the model it's not a radiance. So there is some translation that has to happen. So all these sorts of details go into the evolution of data assimilation techniques. And the best thing we can conclude with here in this short podcast as an introduction is that Data assimilation techniques are evolving, and data assimilation speeds and the accuracy of the analysis given to the forecast initialization as well as correction of forecasts along the way are improving. So data assimilation is something that is very computationally heavy and evolved along with the models, and models evolve independently to improve clouds, parameterizations, or explicit representations of clouds, resolutions, and so on. Data assimilations evolve, observations evolve, and then all of them have to be brought together for expanding the horizon of skills, both for weather and climate forecasts. Okay, I hope it makes sense what I said.